Hello everybody, hello from your favorite artist electronist, Mr. Q12, with a very interesting project that I'm having right now. And it is still in development, it is still not finished yet. It is and it is not finished in the same time. I'm not decided yet if I should use it as it is or if I should take another way, another direction to build this project with some other chip. That's the problem. So let's get into the business. Let me start with 4017 chip because this entire project is around it. This is a basic operation of this chip. So when I'm clocking from this pin, you can observe here this red dot that is moving down. It's actually moving up because it's counting up. It's 0, 1, 2, 3, but is shown like it is moving down. When it is reaching this point, it is trying to step up another point, but the other point is non-existent, so it's jumping back to 0. So this is what it's doing. This is the operation of this chip. When I'm clocking from here is literally stepping one by one all these pins, all these outputs. And from here is enabling the chip, this pin. If I'm setting it as high, when I'm clocking, nothing moves there. It's like freezing the chip. EMR, it means must reset. It will reset from whatever point I'm in, it will reset back to 0. So when I'm clicking this once, it will jump directly to 0 and that's it. These are the settings pins for this chip. Carry output or clock output, you can name it whatever you want, is to link other chips. This is an example when this clock output is linked to the next clock. And you can actually do a sequential counting. You can count until a certain number. Let's say I want to count 1, 2, 3 times and then reset back to 0. So you are following this little red square that is moving around because this master reset is set here on this pin. So the functionality of this chip is what I like very much. I really like it. I'm insisting on this chip a lot of times. I mention it, that is my favorite. But in reality, it's not really that my favorite. 555 I see is one of my workhorse, let's say, that I don't mention it as much as this 4017 as I wished for. But that is actually the most favorite and the most used chip in all my developments, in all my history of experimenting. And this 4017 comes very late in my development and I kind of attached to it for convenience. It is one of my favorite because of its functionality, but the pinout, in reality, how it is used, how you have to link all these pins, it's a bit it's a mess there. I don't like that, but the functionality, I like it very much. Why I'm saying all of this is because in all my history of doing stuff and experimenting stuff, I hit this wall that I wanted more. And this is what I'm saying. I was dreaming on a chip that was doing the same functionality as this 4017, meaning counting up all these pins when I'm clocking, but also the reverse order of clocking. I actually have an example. I have another chip that I can show you exactly what I mean. First to find it. So let's see. Yes, this one. Yeah, I can open it. You can observe how fast it's opening. Do I have anything around? No. Good. This is what is doing. This chip 4110 is doing kind of the same thing as my 4017, but is doing it a bit more smarter. It is having two clock pins, this clock up and clock down pins, and also here a reset pin. Okay, so when I'm clocking up from here, from this specific button or clock input, you can read here in the title, decade, up, down, counter, or divider, whatever you want to call it, specifically to drive 7-segment display. So this is actually is not lighting up one single pin, but it is already decoding all these pins to shape a number. So when you are clicking, when you are counting up, you are actually cycling from 0 to 9, and when it's reaching 9, here is going back to 0 and it's starting again. Now I'm at 5. If I'm pressing down, it will clock inverse in the reverse direction. So 9, 8, 7, and 6. So this ability of clocking up and down is very, very appealing to me. And I really wish I have this kind of chip in this bit form, counting bits, because all these pins are exactly what I'm calling them. They are bits, calling one bit at a time, making it high. And then is having this reset. When you clock this pin, you get to the 0, exactly as here. I showed you that 4110 chip to give you an idea of what I'm expecting from this 4017. This is what I want from this chip to have. I really want it to have this functionality of up and down counting, and also having this enable pin, also this reset pin, the carry out pin as well, but also have this up and down clock, and not only one single clock pin like it's having this configuration. This was the idea that make me start thinking on another way of doing it. Let's actually look on 40,000 series on wiki. List of 4,000 series. There is a list actually here. You can see this parts list. I looked and I searched everything in this 40,000 series, and it's moderately long, and you have to check everything. You have to look in the datasheet and so on and so forth. You have to read everything, and I did read everything. Trust me on that. On each and one of them, I probably used the search function of the browser. Let me go back. 74,000 series. Let's see here. This is on Wikipedia as well. So this is the same page as the other one, but for 74,000. This is having a longer list than the 40,000. You see what is having here is a lot. Oh, wow. And again, it took me days to get through all of them, and I did it in time. I didn't do it yesterday. I did it I don't know, in the course of time. This was a very long project that was spanned on different pockets of time. In one pocket of time, I did something. In another pocket of time, another thing, and so on and so on. And in this current pocket of time, I did the actual project. I put my foot in front, and I actually do something about it, because this is a long thought project. I didn't have the courage to start it, and I said to actually make all the homework that I can possibly make. Lucky for me, all this very, very long, quite extensive list of chips from this particular series, they have a lot of duplicates. It wasn't easy, but I'm saying it was a little bit more easy to search because of those duplicates. I kind of knew from the naming, from the description, from here, I kind of knew, yeah, that is very similar with the rest of the others. So it kind of helped me to cut down probably more than half of this entire list to a couple of them that are doing the counting that I wanted. I also searched specifically for counter, for decade counters, not binary counters, and because it's having a ton of binary counters, and both families, both 4,000 families and 74,000 families. The thing is that I did my homework and I could not find anything about it. And in the course of time, of course, I start to think, or better say, to imagine, because I have no proof, but I believe this chip was released, this 4017, this decade counter, it was released in this shape as it is, only as proof of concept, pretty much. Yes, we can do it. And if you want this chip to do specific tasks, yeah, you have it. But with this less functionality, I start to believe, and this is a conspiracy theory here, I start to believe there are actually that kind of functionality that I'm mentioning here, that I want with two buttons, with two clock buttons for up and down. I believe they are in existence, but they are not made public, not for everyone. They are like a couple of them, and they are not that well known. They are known only in a very obscure circles somewhere on this globe and somewhere in time. I'm not sure when and where, but this is my conspiracy theory side of things. I start to believe there is an existence such as chip, but it's not for everyone. And that is, well placed for certain people, not for everybody. For everybody is this 4017 that I'm always praising, and I'm always saying, what a nice chip it is. It is nice, but to a point. You can do some interesting stuff with it, but again, to a point. It's not that perfect. I really wish there was such a thing, such a complete logic chip with complete functionality. My idea was to have one single chip that is doing all of this, because you can actually do what I'm saying with a binary counter. Let me show that as well. Boy, this movie is getting long, but it is a complicated subject, and I want you to understand how complicated it is and how many lengths I walk. And I tried. Basically, I know some stuff already at this point from all this research, from all this concentration on this subject. So I learned quite a lot of stuff about it. And it's good to make yourself some plans and to follow a little dream like I'm explaining and like I'm describing here. You will learn a lot. And it's like child play. At least for me, it is like that. This is how a child is thinking when he's interested in something. He's researching everything that he can, learning in all this time, in all this process. Okay, enough about the child mentality. Let's search for binary. Let's see what is giving me. So I believe this is a comprehensive list. When I was searching all those Wikipedia lists, all this list, I made this long name file with the most important ones that I could find there in those lists, and also here in Proteus as an integrated circuit to actually test it. And I find out some very, very weird functionality of some chips, like this here. Decade option is not what you expect. Counting in binary to 10. So it is counting to 10, but in binary it's not actually counting on 10 pins, like 47 pins. Yeah, it's a shit. So 4029. So 4029. Yeah, it's called resettable up-down counter, binary or BCD decade. And BCD, it means binary converted to decimal. It's converting the binary into decimal outputs pretty much. But this motherfucker is not what I was expecting, at least. I was expecting 10 outputs. But when you clock it, as you can see, that was 1, 2, and now 3 is 2 of them. Yeah, you see 2, 1. And the next 4 is this output C, QC. Yeah, you see it's jumping here. So it's counting in binary. But here, when you read it like this, you tend to believe this BCD, it will actually count 10 pins. But in reality, it is counting in binary, but up to 10. And I had to actually test a ton until I figured it out. Trust me on that. It was not easy to figure it out. And I didn't find anything on internet to show me these little details that I'm presenting that I already discovered here. If I find something about it, it was very, very obscure. It was hard to understand. It was not direct as I'm explaining, as I'm showing to you here. 74192 is counting to 10, but the other one is counting to 16. That's the difference between them. But they are having exactly the same pins, the same functionality, and they operate the same. This is having up-down counter, as you can see. So this is how it's counting, but it's stopping to 10. So right now is 8, there, 9, and 10. And at 10 is resetting everything, as you can see. So it's not counting all the pins. And this one is actually counting to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, is resetting at 16. Like I mentioned already, and probably you've seen it here, you need to decode, you see it here written in blue, you need to decode this binary output into a real decimal. So you have to add another chip here that is converting this binary into decimal. So for that, you need a BCD. Okay, let me search for BCD. BCD. 4028. When I'm having 1, is switching to this, as you can see it here. This is A. You can see it here on the table. There is. And when it's all 0, you have the first bit, which is Q0. So if everything is 0 here, is this one lit up. And if you lit up all the pins, actually you don't have to lit up all the pins to enable all the pins. You have to enable only until 1010. So 1001. So this and this, and it will jump here. And when you switch to 1010, nothing is lit. Either you do this, or actually you can do that 1100. I believe that one. No, not that one. This one. So is also off. So what it's doing is converting whatever binary number you have here on the inputs and is counting in decimal output. Because this is actually counting, as you can see here in a line, this is a diagonal line of 111, but everything else is 0. So it is having from 0 to 9, you see, from 0 to 9, it means 10 successive conversion or steps. So it's pretty much is doing what my 4017 is doing. So what this is doing, this is counting in order, one by one in binary, and this other one is converting into decimal, like my 4017, and is decoding all that up and down counting that this chip is doing. This is a little page in all my homework that I did so far about this subject, and I'm telling you, I learned quite so interesting stuff about logic circuits and how they are operating, and many thanks to Proteus simulator that I can visualize it, that I can test all these chips. It is having quite a good amount of database of chips, but they are not all functional. But I discovered some other newer version of chips that this Proteus database is not having it because it's quite old, and it is dealing with the classic integrated circuits. Let's say they are classic, but there are newer integrated circuits that are doing better job or better functionality, or new and interesting functionality, or new and fucked up functionality compared with the classic ones, let's say. But this simulator is having some limits, and we have to deal with these limits. This is a page in all my research, in all my fight to discover this glorious chip that I'm thinking it should exist, and it is not. That is having up and down and is converting automatically inside into decimal and not in binary. Practically, I can use 2 chips and make this up and down functionality using 2 chips. But my idea is to use one single chip that is using this up and down clocking and counting in decimal, switching this one single bit on these outputs. Now you probably understand why I'm saying that this particular chip 4017 is one of my favorites, because it's doing a very simplified operation to compare with the other chips that you have to use multiple chips to have the same functionality. This is one single chip that is doing a lot of stuff internally. That's why I like it. Again, it's not really my favorite, not really my workforce chip. My workforce chip are other chips like 555s and other chips that I'm using them more often than this. I really want to find a very good functionality for it, because I have 100 pieces of them, but I buy them because they were cheap enough, and because I'm saying I like this chip, I said, well, put your money where the mouth is and just buy a couple of them, more than the 10 pieces that you usually take for each interesting chip that you find, because this was my mentality. They are not that cheap if you are taking them in bigger quantities, but 10 pieces is cheap enough. If you buy only one chip and you burn it and you wait 2 fucking months until it's arriving, that is not a good or smart idea or mentality to have either. So it's good to have at least a couple of spares, so like 10 of them every time when you buy something, buy in 10s. I step forward and I buy even more. And now let me switch to reality and actually show you the chips that I'm having, that I received quite recently. This is my actual box of chips, new ICs, and voila. Voila. A very nice opening. And here is literally full of chips. 4017, I'm not sure where you are. This is a deep package, and on this other side as well, and I have not 10 but 20 of them. So these are my dip chips, and I wanted to show you the context, all these other chips that I'm having. All right, so I close this box. I'm having this new acquisition, but this is a soft package. This is how they are looking here. 100 pieces, very nice. I tested one. The first thing when I received them, in the same day, I took out these adapter boards, and it was having a lot of wires here and some LEDs, and I tested the shit out of it. Here is a wire that is connecting to ground. This is pin 16 is here, and this is the positive, is this pin here, positive pin, and this is the negative, the last one here, and is linked here. And these other two are here, reset and clock enable, and they are going to ground, both of them. And as you can see here, they are linked to this with a long wire. I had some very strange problem from the clock source that I was using was not strong enough, and the chip didn't work correctly. And I thought, hoppa, I'm having a ton of busted chips here. I wasted a couple of good hours, 3, 4, maybe 5 hours, until I figured out that my clock source was shit that I was using. And I switched with another clock source, with this clock source, with the 555 as well, and this was doing a great job. And also this debounced button, I was manually clocking, this is the clock input here, and I was manually pressing this button, and it gave me the normal behavior, the normal outputs. It's a fine chip, it's absolutely fine, but be careful with shitty hardware that you are having. You are drawing the wrong conclusions. This is the story and what happened with this particular chips. In the very first day when I received them, the first thing was to test the motherfucker and to see if it's wrong or if it's good. I really don't need them, how many they are. But like I said previously, I put my money, and this is my money, where my mouth is, because I said numerous times that I like it. I said I should have a bunch of them, more than those 10 or 20 actually. Why I'm showing you this this box of chips here is because of this SOP package, this very small package form or shape or dimension. And I really like this size. This is a nice size, and I wanted this chip to have it in this size as well. And I thought, if I'm buying 10 of them in this size, I will probably not be that happy. And I said, well, fuck it, I will buy 100 of them in this particular size that I like it. And I like it because it's occupying a very small space area. It's very shitty to link all these output pins. But I'm also having these prototyping boards or adapter boards, how they are called, and I can make use of maybe. Usually I'm not using them. I'm using directly the chip glued to the cardboard, and then I'm dragging directly from their pins the wires, if I really want the space. But if I'm not concerned about the space, I can use some adapter boards like this. Probably. I'm not sure what I will do in the future. But what I really like about them is very small size. And that's it about it. Okay, so this is all I wanted to talk about, the chips, the ICs, the physical IC, and let's get to the actual project right now. Let me close this. I hope I didn't forget anything important. I'm having this, let me actually use this shortcut here. So you see here in the electronic my IC microcontroller ATTINY44 UpDown Deca counter. It means this UDDK UpDown Deca counter naming that I used in this folder. I'm using this ATTINY44 microcontroller to make a better 4017, pretty much having this clock up, this clock down, and also the reset button. I made a couple of codes until this last one that you are seeing it here, which is this one. I'm using it right now for this finished project, what I'm having right now. But this file, this saving file, and this older files, these are the history until here, and this is the same as this one that I'm testing it right now. But I'm keeping it here just for the naming, to know exactly what I did, because this file will get overwritten, and that's the logic what I'm having here. So I made all those iterations because I changed a lot of wiring. I actually changed where the buttons and where the LEDs should be on this chip a lot. I'm telling you, I spent probably 2 days only changing them, thinking where to place them the best I could. This is the comparison of the 4017 pin out here, and I really don't like its pins, the way they are mapped internally. And what I mean is output 0 is on pin 3, output 6 is on pin 5, output 4 is on pin 10. What the fuck? So I wanted an orderly mapping of the pins. Like this is 1, it will be output 1. This is pin 2, this will be pin 2, output 2, and so on and so forth. That was one of my priorities. Another priority was, where the hell should I put the clock up and clock down pins, these two pins. This 4017 is having 16 pins, you see, but this ATTINY44 is having up to 14 pins, so it's missing 2 pins, which are crucial for this entire project to work. But more than this, I discovered something else not nice. You will see this PB mentioned a lot. It means port B. One microcontroller is having one or multiple ports. A port, it means it's having a series of pins that is controlling. So you can access those pins through this port. Port A, port B, port C, whatever the number is having. But this ATTINY44 is having 2 ports, port A and port B. And you can see them actually here. You see port A, pin 0, 1, 2, 3, 4, 5, 6, port A 6, port A 7, and that's it. It's having 8 bits in this entire port A that is responding to the output pins. And port B0, port B1, port B2, port B3. So these 4 bits, instead of 8 bits, is having only half of them. It's having only 4 bits in the entire port. And this is how it's structured. It's having these 2 layers of 8 bits pretty much, because this port B is also having 8 bits, but only 4 of them, only half of them are used. The other half are non-existent. They are not used. Most probably they are implemented inside the chip, but they are not used at all. Only these 4 bits are used. And port B3, this pin, specific pin, I actually mentioned here is pin 4, as you can see, of the chip, the physical pin 4 of the chip. 1, 2, 3, 4 here. So it means this port B3. And is this reset in yellow? You see it here? No. So after I compared everything, after I decided what pins I should use from this chip, compare with the real chip, the 4017 one, I reached the conclusion that I'm limited on the pin count and the pin options. So these 2 pins are 1 and 14 are reserved for the power. These are power pins for the chip. So I cannot use them. The same as this decade counter is having this pin 8 and pin 16 are reserved for the power for the chip. And we cannot touch them. So here on the microchip, I have 12 pins to deal with and to use. So 12 digital pins. This gray marker here, it means a digital pin. When you are having a digital pin, it means it is an in-out pin. You can send and receive data or current or certain amount of voltage on all these digital pins, all these in-outs. But is a catch, is a problem specific to this pin 4 that is using this reset pin. And I raised this problem here, how to set ATTINY44 chip PB3 pin 4 reset pin as in-out. So important warning, disabling the reset pin turns it into a general purpose in-out on PB3. But you will no longer be able to reprogram the chip using ISP in-serial programmer unless you have a high voltage programmer HVP. In-serial programmer is done using Arduino. I am using Arduino with a special library. I actually mentioned this. I'm making a program for ATTINY44 naked IC that I'm programming with Arduino Uno R3 as in-circuit serial programmer using ATTINY core, specific for this family of microcontrollers, ATTINY family. So as you can see here, I'm using Arduino Uno R3, but here is saying that you cannot use ISP using Arduino. So you have to use something else, another programmer, to be able to reset this pin, to enable this reset pin, to be able to use in-circuit serial programmer with Arduino to be able to program it normally. So this is a very big problem. This is the first time I'm encountering it, and it's a shit. It's very, very, very shitty. This is actually called a fuse. This is a real fuse. This reset pin, this is a fuse that you can defuse it pretty much. You can set it off, this reset pin, and you can use this pin as an in-out like the rest of the other pins, but you cannot program it normally with Arduino Uno. You have to program it with something else. That is a bit over my ears. I never encountered and I never used such a device. This is the first time when I'm hitting this wall, when I'm seeing mention this high voltage programmer. I actually know about it. I know it from other chips, from other microcontrollers older than ATTINY44, like PIC microcontrollers, 16F84, I believe. And I believe it was using a high voltage programmer for some very, very specific thing that I don't even remember what it was, but I remember something very, very vaguely. In all the history of using microcontrollers, I'm not using microcontrollers daily all the time. I'm using them from time to time. After a couple of years, I remember, I know how to program microcontrollers. I should try it again, but hold on. I have to relearn everything. I have to remember everything. That's the case for me, at least. So I'm the average Joe that is programming from time to time, not every day. That's the problem. Okay, so this is a very, very big discovery and a very, very big problem. And I spent half of a day, probably 6 hours or 7 hours until I reached this very well put, this little conclusion. I had to read a ton and I had to concentrate a ton on a lot of stuff until I get to this issue, until I realized it's actually a very big fucking problem. And then I put it down here on this forum and I discussed with the guys here on Arduino forums. So one of their solution was this here. So PB3 pin 4 reset pin can be used as an analog input with a limited range. The input voltage should never drop below half of the VCC with a safe margin, or the ATTINY will reset, but it is not hard to use it as an input pin that way. Just some voltage division will do the trick. But later in our discussions, he is also mentioning, oh, sorry, on ATTINY44, the reset pin is not connected to ADC. But I actually managed to make what he is saying here. I managed to build the circuit, this divider. It's a bit more complicated, but it kind of worked like this. The problem was that I was not getting the code response. In hardware, I could make some simple test of switching two LEDs, I believe, from all this experiment. Let me check. No, I don't have that. I changed this file a ton of time, and I didn't save my previous experiments. I only took these pictures and that's it. I cannot test it for you. I actually put to heart what he is saying, although I didn't realize that he believed this reset pin was an analog input. But in reality, it is not an analog input as the rest of the pins. And how do we know which pin is analog? It is actually mentioned here, ADC, it means analog to digital converter. ADC is 0, and they are actually hand in hand with port A. So all the pins on port A are ADCs, but on port B is not having any kind of ADC. So he probably looked in the datasheet, he's seen this ADC is mentioned, and he automatically thought this pin is also an analog to digital, but it is not. I actually mentioned it here. Reset pin not used. This pin 4, I'm not linking it to anything. I'm not using it, and it is cutting down the pin options that I'm having even more than it was before. Like when I compare the two chips, this is having 14 pins. This is already having smaller number of pins, and I have to conscientiously leave this pin untouched, unused by anything, because this pin is used only to program the chip. From 12 pins that I was remaining, now I'm having 11 pins to work with, and I'm having 10 LEDs to lit up. So I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 LEDs, and I'm having one single pin remaining, PA7, port A7, or pin 6 of the chip, and is this one. So you read here, port A7, and that's the only pin I can put a button on it. Again, I will repeat, I want to use one single chip with all the functionality as this 4017. So that's what I'm doing here, but I am forced literally to use smaller number of pins, and I don't have enough pins to use it like a normal 4017. I did find a solution, although, to finish with this kind of work, it kind of switch something, but it was very dubious what it was doing, and sometimes was working. I had to use 2 switches to be able to perform the correct clocking on that reset pin, so it was a pain in the butt. No way, Jose. But it was kind of working, but weirdly, very weirdly. And I concentrated on the next option, which is actually using an analog pin from port A, one of these ADC 8 pins, to use one pin as an analog to digital converter. So literally to read an analog value from 0 to 5 volts, pretty much, and to convert it in binary, but in code. So this is what I did here. I'm using one single pin, and I choose this last one, PA7, port A7. It is this pin here. On pin 6 is port A7, is the last port, because I wanted to retain this numbering system. Port A0, 1, 2, 3, 4, 5, at least on this side, to be a bit more easy to operate, to use all these outputs in order. And until actually here, this is in kind of in the middle. This is not used. So I'm having this pin, and the next is this one for the LEDs as an output, and this and this. And that's the order. That's why I choose this last bit from this port A, and you can see it here. Port A7 on pin 6 is linked to all these buttons. Actually, I should take out this because this was automatic. Let me actually show you the functionality right now. So when I'm opening the chip, is resetting there to port A0. When I'm clocking up, it will go down. I have to switch like that because earlier I was having this automatic clocking. That's why I put this extra switching. When I'm clocking up, so this is what it's doing. And I'll do the entire sequence. And this is on port B, and all these LEDs are on port A, and there are 7 of them on port A. Remember, port A is having 8 outputs, and only 7 of them I can use, because the last port I'm using for these buttons, the rest 3 are used from port B. And let's clock down. This is going down inversely than before, and let me do it somewhere randomly there, and when I'm clicking the reset, is jumping automatically to 0. So this is the entire functionality that I really wished in a single chip. Again, I'm insisting on making you aware of my intention. This was the entire idea, to make a single chip that is doing all of this stuff, clocking up and clocking down, and with a reset, and to output in a decade fashion, not binarily, which is pretty convenient and pretty nice functionality, and this is what I was after. Let me put a parenthesis here. I was discussing this problem with my friends from electronic forums. The only option that they suggested to me was to use a microcontroller. But I already thought of this option, and I actually make it clear to them that this is the expensive option, what I'm having right now, using a microcontroller just for a simple logic circuit. And it's a very expensive chip for just a trivial functionality that I can get it from a 4017. Effectively, the only suggestion that I get from them is to use a microcontroller, because there is no such chip available, at least to general public, from what I know and from what I searched for. Let me actually show you a little bit. Is there another logic chip similar with 4017s, but with up-down counting, not only up? And here I'm mentioning this is the price for 10 pieces of ATTINY44A. Okay, this is my chip here. I paid $12, including the shipping, and $20 for another 10 pieces, but for Atmega 328. So I'm having these 2 chips from Atmel. So it's a very expensive. If I'm fucking up one component, if I'm destroying, if I'm burning an IC, in all my crazy experimentation, if I'm not careful enough and I'm burning them, 1 or 2, I should not be put to the wall and be incapable of doing anything else after that. That's why I like to have a lot of spares. It's a very nice mentality. It's a very nice philosophy. It's a very good thing to have and to work with like that, to have a lot of spares, not to be afraid to burn 1 or 2 components, because stupidity is an intrinsic power of humans. This is our greatest power. It's like hero power, you know, being stupid. And we are excelling at being stupid. We are making stupid mistakes every time. And the school is teaching us that is not good, and it's a sin to make mistakes. I'm showing you all this pricing because I'm comparing with the pricing for 100 pieces for my 4017s SOP 16, the ones that I showed you on my working table, those tiny smaller ones, and I paid $8 for 100 pieces. It's very cheap. This is very cheap. And another guy, after I demonstrated how expensive is a microcontroller, trivial operation, a normal operation, this is not a very complex operation that a microcontroller should do. Yeah, check this out. Look at these things. Let's see what he is referring to. But I never seen this. Is a RISC-V microcontroller QFN, which are very small. I believe 50 of them you can put on one finger space. It's like they are super small. So SOP 16, these are better, and SOP 8, these are better spacing, and the pins are okay. And he is showing me that these are very cheap for 10 pieces, $2, $3, plus transport. Yeah, actually, let me add this to cart. So 3 here for the product, and another 3 for the transport. And let me remove it. So this IC, I have no idea how to work with it. I do not have a programmer. I never heard of it. It's a very new chip. And I will love to learn program other brands of chips, of microcontrollers, different from microchip PICs. For the moment, I am very extremely pleased on programming Atmel chips like this ATTINY44 and that Atmega 328. So these two chips I worked with, these two microcontrollers from Atmega, and they are a breeze to work with them. It's very user friendly. You have no idea how easy it is. It's my recommended chips for the beginner, because me as a beginner, I started with the PIC microcontrollers because there was nothing else better than them. They manipulated the market for a very long time, or at least from my times when I started, when I began with the entire country here in Romania. They were up high with them. They were acknowledging them. They were saying they are the best. They are the only chips, microcontrollers, microchip, PIC microcontrollers. They made me believe there is nothing else out there, no other alternatives. But time passed, and I discovered very late, extremely late, I discovered the Atmel chips, unfortunately, to my shame. And that's why I didn't do anything great. I didn't build anything more important with microcontrollers, because I didn't know about their fucking existence. I didn't know, I swear to God. And this is me, the average Joe that is doing it from time to time, is not using them all the time. So that's another important point to make. So this is his option, but it's not a good option because I have no idea what this kind of chip is. I never work with it. I will stick with my prices and what I know. All right, so that's about pricing and the amount of chips that you can use. So I'm closing the parentheses, and now we will continue. Boy, this is a long fucking video. I knew it will be a long one, but I don't know. I don't know what I can cut from this movie to make it shorter. This will be a problem. But this is an interesting subject, I believe, and it will be interesting for some. Let me show you very briefly the codes. Like I said, I made so many changes. I changed the LED pins. I changed this input for the two buttons input pins. I changed them all around, especially here on this pin 4, to give you a context of what this code is doing here, what I use it for. And this is a copied from internet. I didn't make it. I'm not at this high level what you are seeing here, but this little fragment of a code, it actually worked, but in one condition. And it was this condition: when I'm going into the settings of this chip here. So this is the settings for this ATTINY44. You can see the name here. And these are actually the fuses. This one here, it says reset, it means reset, disable, external reset disable. Is this pin 4 that right now, when my program is running correctly, is unprogrammed, is set to 1, and is set to unprogrammed. But when I was setting it to programmed like that, and I was running this code, actually it worked, because that fuse was set. It was programmed, it was set. And I didn't realize it in the beginning when I was playing here. A couple of hours it took me to figure it out, to understand that this is actually a fuse, and that is way much more low level than what I'm usually doing when I'm programming through Arduino. So that's this code and how it was used. It was a bit tricky, but it helped me figure out this little problem, this reset problem on this particular chip, and probably other chips as well, most probably. I actually put in the naming what the program was doing. PB0 is actually this pin here. So port B0 set as input correctly, but not the rest of the pins. With port B3 reset pin, good only in simulator. Let's see this other code. Probably this two, I was using port B0, which is this, and I was using it as input for the buttons, and I was trying to use port B3 as an output to lit up a LED, and I couldn't. I was getting an error every time. These are the first two tests. So this is UpDown. This is the code. I was stepping in and out from this header avr inout.h. So I was dancing around it, because I also realized something very, very interesting. The usual Arduino code is like a shell, and is helping very easy to work with shell. But underneath this shell, there are other headers that are a bit more harder to work with and to understand and to learn them. So that's what my realization was by dancing around this header here. This is the code that is using this header. From this code, I was using, you see, this one as well. This is the same library, and all this DDR and DDR and port B, port A, you see here mentioned, they are from this header. They are specific keywords and specific way of doing things, specific from this header, and you have to initialize this header to be able to use it. And I learned this other little detailed about all this entire project. Like I said, I learned a lot of stuff. And yeah, I kind of like it, and I kind of stick with it, because it's an interesting way of doing things. And then I leave it there, this header, and I used only this DDR and DDR here. And here, this code, which is very small code, I was testing specifically only this port B3 pin, which is this one. So after I didn't manage to make it lit up an LED because it cannot be set as in-out, I tried to, instead of outputting to a LED, I tried to input from a button to it. So at this point here, when I was doing this code and I was doing all the hardware schematics that I was having, but I'm not having it right now because I deleted it. But back then I was having it hooked up to this pin. Yeah, I believe this pin 4 is here. You see pin 4. So this is pin 4 part when the button is pressed on this specific pin, and it worked like in the name. Like here, port B3 reset pin good only in simulator because I activated this little fuse here, and after this I realized, and I made another code here for some reason, I don't remember. It's probably a continuation of that one, and probably at this point I realized that is a special pin and I have to avoid it and I have to remake everything. Imagine the frustration. I worked 2 or 3 days only on this problem to figure out how to link the LEDs to which pin and how to put those buttons to which pins to add them, and then to discover that I cannot use all the pins. And it took me around 2 days, 2 or a little bit more than 2 days for all this old code that you are seeing it here. And this file here is the current code that I'm using it right now, that you've seen it working, at least in the simulation here. And this is how it's looking. I comment out the older code that I was using because I changed it quite drastically. I'm still using this inout.h header. It is coming with Arduino. You don't have to download it from anywhere. It's part of Arduino program. It's very easy. Just include it here and you are good to go. And here is where I'm using directly. I'm talking with the chip and I'm telling him what to do in binary, because this is the most easier to visualize way, at least for me. This is how I'm visualizing, very, very easy per bits. Binarily. This is port A, which is having 8 bits, and this is port B, which is having also 8 bits, but is only using this 4 bits, but these other 4 bits are not used, they are not implemented. Only half of this entire byte is implemented. So in reality, is like I told you before with these pins here and here. Port A is having 8 pins and port B is having only 4 pins, if you remember. And also here on this diagram, you see port A is having these 8 pins and port B is having only these 4 pins. This binary representation is extremely helpful to visualize the pinout of the chip, at least from the port perspective. So pretty much I'm setting here to reset to PA0 to make it high every time I'm starting the chip. You see one single bit is open there. So port A is lighting up only 1 bit and everything else is low, is keeping all the outputs low. The same for port B is keeping everything on low. Doesn't matter what is having there. If it's used or not used, doesn't matter. If it's input or output, also doesn't matter. Actually on port A, this specific bit, this is the last pin that I use it as an input. But I'm setting the entire port A as low because this doesn't matter if it's low or high because it's an input here and it will not listen to this command. Only the outputs will listen to this command. You can command it like this very, very easily, extremely easily and extremely intuitive, I may add. At least for me it is very intuitive to set the bits in this manner. That's why I liked this header. It's terminating with .h. It means it's a header. That's why I like this header for this very nice functionality and is cutting down on a lot to write. This is the initialization of the chip, and I'm also declaring that on pin 7, Arduino pin 7, PA7, which is this brown one, I'm specifying that this is the input for the buttons and is used as an analog input, that I'm using that ADC from it. One pin used as analog pin set to read 3 buttons, those 3 buttons which are these ones here. Literally I have an army of resistors here, which I don't like at all, plus these diodes and some other resistors that I didn't account for. So this is the initialization when I'm declaring and specifying everything, and here I'm making an array that is called pin. This is the normal numbering. These numbers, they represent actually the pins of the LEDs, is all these 10. You see starting from 0 and is terminating with 9. It means it is having exactly 10 numbers. This little array, I actually comment them. They are the pins for the LEDs, excepting pin 7, which is, you see it here, Arduino pin 7, which is used as an input, and then I'm continuing on port B. This 8, 9, and 10 are on port B. All of these are port A. And then I'm making a simple function for resetting, very, very easy to cycle through all these pins here. That's why I made this array, to be able to cycle very easy, and it's practically making them all low. And here is the count function, and a very important variable QX. And this QX is used both in this function and also here. You see it here in this loop function, and is using this QX variable and the count function. And in the count function is lighting up 1 by 1 each LED. Pretty much I'm lighting up 1 LED at a time. I'm resetting first every output as low. If my QX variable is -1, it means I'm counting down, and when it's reaching -1 is resetting to 9, and when I'm counting up, when it's reaching 10 is resetting to 0. So that's what these 2 little lines are doing here. I'm having this button is pressed variable. This is a very important variable, so let me explain it here in the circuit. When I'm pressing here, you see if I'm keeping it pressed, this button, this is jumping only 1 time here, you see, but I'm still keeping the button pressed without this boolean, this variable that is used here, and here. If I was still keeping that button pressed, it was cycling very, very quickly through this loop. It was counting very quickly. I could actually was able to see how the LEDs were running very, very fast. And when I was releasing my finger from the button, it was randomly jumping there, doesn't matter where. And this is what this little very, very important boolean is doing here, is enabling and disabling when the code should run and when it should stop. If he is seeing the button is still pressed, it will not increment anything. Only the first button press event, it will count one time, whatever it is, depending on the button press, if it's incremental or decremental or resetting, and it will then stop everything while the button is still pressed. And when he will see the button is released, here, button is released, then is setting this as false, ready to accept the next press, to press it again. And then the actual reading, the code for the ADC is here in this part. Here, this line, this value variable is reading the analog input, which is pin 7, if you remember. So I declare it here, this variable pin 7. This is more for visualization. I could actually put here 7 and I can get rid of another variable in my program. Probably is better like that. But yeah, well, this is called optimization. We're starting to optimize the code. And my code at this point is not completely optimized. It's kind of rough made. It's kind of optimized because I have some experience with it behind me, but it's not seriously optimized. I can optimize it here and there, but not that much. Most probably is already 90% optimized. I can optimize it very, very little from this point as it is right now. And it's checking this value. This value is up to 1023 or 24. This value can get inside this range from 0 to 1024. It's the ADC value that is reading right now. And this is the voltage converted into digital form or digital numbers. Actually, this is a binary value. That's why I'm saying that the Arduino code is very easy to work with, because it's very visual, it's very intuitive, it's user-friendly. In decimal is better, way more better than visualizing it in binary. Although in binary is not as bad as it sounds, but it's a bit more easy to understand it from one look. And I also comment what the function of the button is. This is for the up button and the range of the voltage. And I set it up as 2 volts, 3 volts, and 4 volts. But in reality, you have a range between this. This is button for 2 volts, 3 volts, and 4 volts. So that's the entire philosophy. That's the entire code, what it's doing. And I hope you like it, because I like it, because it's functional. It's very good. Yes, another big problem was the hardware side. As you can clearly see here, my entire page, I did a lot of voltage divider tests. That's why it took me a lot of days until I managed to figure out the values of these resistors. I have here specific value resistor for this 5 volts input to obtain specific voltages that I wanted. This is actually, these blue markers are showing you the actual value. You see, if I'm closing, it's not showing anything, but if I'm opening the simulation, it will show here the reading on this point, and here is showing 2 volts exactly, 3.07, 4.07. So this, I had to play a lot, and it took a ton of time to do it manually, and I did it manually because there is no other option. And I did it for this longer shit, as you are seeing there, as well for this ones. But this crazy stuff is doing, it's actually 0 volts here, but it's a negative 200 number. It's 0 volts actually. When I'm pressing, when it's high, it's actually showing the value. This is also 0 here, is a negative 005, and also this one, a negative 005. So these two are 0. I'm having 2 volts on this branch. Here, I'm having 3 volts here, 3.1 here for this branch. And here, when I'm clicking this reset pin, is actually 4 volts, exactly as my little bolded notes. These are just notes here, here, and here, just to visualize, to be able to see them more clearly. But before reaching this stage, that this is an advanced stage, what you are seeing here, let me introduce you to hell. To the hell. You see here, this name RVD means resistive voltage divider, and I have 3 files of them, and I will show you very quickly. I will get through them, because this is another very important element. This is an older project that I did. I started with this RVD1. This is an older project with rotary switching, with different values for all these resistors, and it was a pain in the butthole, and all these resistor values, and I had to figure out everything manually, and it took me days, literally days. And I have a couple of them here on the bottom as well. Let me close this, save no. And I'm having file number 2. And I also have another bunch of stuff, and I have here also a couple of experiments, and everything you are seeing in all these RVD files, this is RVD file number 2. Everything you are seeing here is made manually, tested a couple of times, and sometimes it took me half an hour to figure out what is the value of the resistor that I should have to get a specific output voltage. It seems stupid to do it like this, but when you are in a hurry, like I am here with my project, I just wanted a 2 fucking volts output, and doesn't matter the value of the resistor. So when you are in a hurry, you really need a quick grab. You need to put your hand on it, and you grab it and you implement it and see the result, the bigger result that we have to pay attention to. So these are the actual voltage dividers made from 2 resistors. I marked their values and all these little blue markers, voltage probes, and they are showing you exactly what this actually measuring here. 0.5, exactly as my label that you are. This is just a stupid label here. I can change it every time. It's not measuring anything, this one, but this is the probe that is actually measuring right now when I'm starting the simulation. 1.500. To obtain this number, I had to tweak this motherfucker resistor value to get me as close as possible to that 1.5000, and I'm having the same here, 3.500, and I have to tweak this resistor value quite a bit. Yeah, that's why some resistor values are out of this world, like this 66666. And if I'm changing one single number here, so, let me put it here, 7. If I'm changing this and run it, yeah, you see I'm getting 2.9998, and I don't like it. Everything you are seeing here, I didn't do it automatically. I didn't ask anybody. I did it myself, and it's a pain in the butt. And this is LVD3 number 3 file, and here I'm having some advanced resistor voltage divider that are using 3 sets of resistors and 2 outputs. So if I'm simulating right now, you can see here 0.50, and here is 0.25. So these are more advanced, and this is actually 432. This is the branch that I was using in my program, and you've seen it here, the branch. And by the way, you can copy it from here and paste it in another save file, which is a very, very helpful and very nice feature of this program. You can copy and paste from one save to another save. So I'm showing this other project because they were part of this project. This was a very complicated project that involved a lot of directions. I had to go and to research and to find and to read and to do my homework and to learn new fucking stuff, and it was hard. It was quite hard, and it was in time, made in time. And when I'm saying made in time, I'm saying in the course of a couple of years, but I didn't concentrate on it all the time. I was concentrated on fragments or bubbles of times. I was having in mind this project in my past. I was thinking I will do this project, and to do this project I have to prepare. I made this resistor project for other projects, but I was also having this project in mind as well, and other stuff that I research, all the logic chips, all the stuff that I mentioned until here. You get the idea that I kind of prepared in a very long time to reach this stage, which is looking like it's a very easy to implement thing. It's obvious that you have to use a microcontroller. It's obvious that you have to use more in-out pins for the microcontroller. But when you have to actually implement it and you have to use the components that you have in your arsenal, you are hitting some walls. And as easy as it appears to be, it is quite challenging. I can assure you, it is quite a challenging project what you're saying here. But I'm using this project also to learn to invest in other directions that normally I'm not interested in, or they are too boring. But having this project or this kind of projects like this one, they are pushing me to not get bored on some very important aspects of electronics, of coding, of researching. You know, it's good to have a project guided by the project to solve it. You will get involved in other smaller stuff that usually, when you read them by themselves, they are boring as fuck, and you cannot concentrate on them. I can assure you that's why I'm making use of this project to get more advanced in some other detail aspects. Going back to the code, this is a very complicated code for a logic chip. Compared with a decade counter like this 4017, this is extremely fast. It's probably, I don't know, 10 megahertz or something like that. A couple of megahertz for sure, how fast this will run. But this kind of chip, my implementation that I did here, it's probably good up to a couple of 100 kilohertz maximum, maybe. I'm not completely sure how fast this ATTINY will run with this code inside it. So it will not be that fast. That's my point. It will not be that fast as a hardware-made logic IC. They are not comparable. This is way more weaker. So that's a very important point to add to the list of having a ready-made logic IC that is doing all of this stuff is infinitely superior to the thing what I'm doing here. Another important little detail is that I had to run automatically with the 5 volts input this pin. So this single pin cannot run with 5 volts directly. You have to convert into 2, 3, and 4 volts, exactly as you are seeing here, to drive this input pin. So it's a bit more harder to manipulate this specific arrangement. This is a bit more harder than I intended. So let me let it run like that. So if I'm closing that one, is running correctly here, up and down. If I'm stopping it and if I'm selecting that one, is running in this other direction. It is clocked from a 5 to 0 volts clocking mechanism, and here is the reset back, and it's functioning correctly. Another very important thing is this. So how to actually run the program into simulator. I'm not actually uploading this code to anything. You see here on the top, it says there upload, but I'm actually verifying. And when you are pressing this button verifying, you see here compiling sketch. And it's doing all this stuff, and it's saying there don't compiling. It means it finished, and it's doing it quite quickly compared with the actual upload. But it is actually doing something else. What I'm interested in this hex, and this Proteus simulator is actually mentioning here is expecting hex. This is a bad way of seeing it, but let me actually show you what in reality it should look like. This is the full name of this file, woodk.ino.hex. This is the actual root. This is a randomly number build. When you open this program, you don't close it after that. You leave it open for a very long time for a bunch of testing programs, and that's why you are seeing these old programs files that you're seeing. I just copied them from here. I Control C and Control V outside of that folder and renaming them and putting them in this folder to save the progress, because I was literally having this program open all the time for about 2 or 3 days. This is the root. You can see it here in the temporary folder, and this is the folder that is mentioned here, you see, and you enter in it, you look for this hex file, because this is the actual name of this file, woodk.ino.hex. You see, my tutorial commander is actually telling you, is showing you that I'm having this extension tab, extension option here to actually see the extension for each file I'm working with. And this is very important. It's not a joke. And you can get very, very confused very easily if you are not making use of that. Like this Windows joke, that is not actually showing the extensions, which I never liked. And I'm in Windows 7, which is a very good Windows. And probably there is an option somewhere to activate that .hex to actually see the extension, but I didn't care to find it that much. Most probably it is. Or some weird trick somewhere, somehow. But this is the default way of seeing. So it's not good. So I'm double clicking the component, and here on where it says program file, I'm going into that button and I'm clicking that folder button, and I'm already in this long folder that you are seeing here. And I know this file, and when I'm clicking on it, is loading it, and when I'm pressing OK, is actually loading this compiled program. And every time I'm clicking this verify button and I'm compiling it new, if now I made some changes and I'm compiling it again, it finished compiling, done compiling, and now my simulator is not running, but when I'm running it, is reading exactly this program. You can actively program here and check here in the simulator what the hell your program is doing. You are checking your program with the help of Proteus simulator, which is a very nice tool to have. Every test program that I did here in Arduino, this is the way I managed to load it in Proteus and to actually visualize it, and then to make the electronic circuit around the code and to match the code, the outputs and the inputs and whatever I needed to use. You see, before I was having another number, so I did stop it and opening, because I don't want to load it here in a simulator too many times. Because it's randomly changing this folder, you have to go and load it every time if you are closing the Arduino program. But if you leave it open all the time and you compile it, you change the code and you compile it, and you leave it on all the time, you don't have to change from here every time. So that's the trick. All right, so the last part of my discussion is the actual implementation, if I will actually go with this chip and with this design that I made until here. And I'm very, very uncertain, and I'm very undecided if I should actually do it like you are seeing it here. I can do it, I can make it in reality, no problem, especially that I don't have to deal with this PB3, this reset pin. Like I mentioned before, that is a fuse. So I'm not playing with the fuses of this chip, but it is in plan. It is an option, and I'm contemplating it. I'm thinking maybe it's an option and I should use it. If I will use this option, all this army of resistors and diodes that you are seeing here will disappear, because this is the advantage of putting the inputs directly on the pins of your microcontroller. You can put 5 volts directly on the pin and not split it in 2 volts, 3 volts, 4 volts like I did here, like the ADC is reading, specific to be read by the ADC. So you can actually put 5 volts directly with here on the pin without any kind of resistor, and exactly as in the real chip, you can clock the real chip with direct 5 volts. And other chips like this, like the other one, 4110, this is a very nice feature to have this kind of functionality, to be clocked directly with 5 volts directly on the pin without all this trouble. This is very ugly and very troublesome. But so this is why I'm balancing a little bit. I don't know what to do at this point, if I should push further into the rabbit hole to change the reset fuse of this chip, and that will be a lot more harder to program after that, not the usual way. But I will have this very convenient input way, but I will have only 2 buttons that I can use, only clock up and clock down buttons, and that's it, without the reset functionality, if I will do that. But it will be convenient from one point of view. This way of doing things is a bit more complicated by using all this army of resistors and components, and also this one. So I will include that one as well, and also some other resistors that I didn't account for yet. That will be a surprise later. I'm thinking, I contemplated this option because I like the idea of having multiple buttons here, to have 3 buttons, and it's very nice to have this reset button. It's a very nice functionality to have, and because of this extra button option, I'm inclined to use this form like you are seeing it already made until here, and I'm counting that I will build everything with very small components. So the footprint, it will be very small, and the buttons themselves will be relatively big compared with these components around the button. So the button will be big, how I'm visualizing, how I'm thinking at this point it will be. So this will be the button. So this is a circle. Inside, this is the button. Don't laugh on my circle. And all the resistors that I'm thinking, they will be as SMD resistor like this, with the two pads on them. They will be around this button, somewhere like that, you know, the SMD components. And probably an LED somewhere, I'm thinking, for the button when I'm pressing the button, an LED with its resistor. This is how I'm thinking. This is a module that will contain all this, and whatever I will add there. This is my vision. This is how I see it, that I can actually do it. All this part here. So it will be a little bit inconvenient from the construction point of view. It will not be as easy to implement it as a 4017, like you are slapping a button on the clock input and that's it. But I am inclined to close my eyes on its complexity, on all this army of components, on all this complexity only for these buttons, because of this third button functionality. That's the only thing that is keeping me to jump on the other way, on the other option, to change the fusing of this reset button and to use only 2 up and down buttons, and that's it. Another problem is to leave aside, to not use this ATTINY microcontroller at all, and to use something that is having multiple pins, way more inputs and outputs than this ATTINY44. But the reason why I'm using this particular chip is the shape of it. It's looking like this counter. Although it's not having the exact number of pins like this, but it's looking like it. It's long like that. It's small like those SOP, because I have those SOP versions. While my Atmega 328 chip is not looking like a logic chip. It's looking like something else. And I'm aware I'm having a lot more input and outputs, but all that I care about is how it looks. I really like the shape of it and the form and how it's looking compared with this one. And I don't like this shape compared with this one. That's my mentality. This is how I'm thinking. This is why I'm not jumping very quickly to this shape and this chip, because it's not visually pleasing. That's why. Because I'm an artist and I like to have beautiful, nice things. Another option, and this is the final option that I didn't research it yet, so I have to spend another bunch of time in researching, is to find another chip that is having a whole lot more pins than this and this. So to have maybe 20 pins or maybe 16 pins. So if my chip was having 16 pins, so these two are power rails. I'm left with 14 pins now. So these are the LED pins. These 10 pins are the LED pins, the output pins. Okay, so with blue, I will have the reset pin and 2 clock up, this one, and clock down. And then I will be left with another pin. So it will be this reset pin that will not be used at all. So theoretically, with 16-pin microcontroller, I should pay attention to have all these pins to be in-out, digital pins, and 10 pins to reserve to outputs. Only 3 pins, like I did it here for reset clock up and clock down. But my decade counter is having something else. It's having this carry out. And the other chips, 4110, is having the carry out for the up and carry out for the down. So when you link 2 together, you can drive 2 chips. One chip can drive another chip under it or next to it, pretty much, from this carry out pin. But this is not really such a big functionality concern to me. To be absolutely sincere, I really don't care. It's nice to have it, but I will not cry very hard not having this functionality. So that's where I'm standing. But it would be good to have every possible weird functionality. So this is the last idea, is that I am considering to search. I didn't put any time into researching for such a chip, but I want it to not be from microchip PIC microcontroller series. I want it to be from Atmel chips and to be big enough to have a good memory inside, at least 16 pins like the original 4017 is having, but I really wish it was having a bit more pins than that. 18 is good, but 20 pins is better. 20, even 22 maybe, and also having this shape, you know, rectangular shape, not the square shape like Atmega 328. I really like SOP versions of packages. They are okay. They are very okay in terms of dimension. Deep packages, they are okay to work, especially to test with them, but if you plan to make something look nice and feel nice, small enough, they are a bit too much. I'm using them, but not that much. That's why I bought 100 of 4017, because they are very small packages. That's why. Like, I hope you understand my reasons and the way I'm thinking and the way I'm doing, because I am the designer. I am looking on these particular things, and they are important to me, and that's what I'm explaining, and this is what I'm telling you in all this discussion, in all this monologue that I'm doing here. Okay, this is it pretty much for the entirety of this movie. It was a long subject to discuss because it ramificated in a lot of other places to cover, and I did my best to cover everything. I hope I didn't forget anything important. And the way I'm doing things, the way I'm thinking, the way I'm planning, and the way I'm doing the stuff that I'm doing is also helpful for you, the viewer, the young designer, I suppose. I hope it's helpful for everyone that is watching my movies to get the feel of it, to make more interesting decisions. And when you see me doing it, you will start to think on your stuff, and it will be a bit more helpful to you. I didn't have this kind of help myself. I didn't hear anyone talking like I'm talking. That's why I'm talking like I'm talking. I'm talking like this because no one told me this detailed. Nobody showed me this detailed, in this such great detail, everything that I'm presenting here. So this is my, in a way, is like a reaction on the stupidity, imbecility, and the idiocy that I came to cross over in my life. And I didn't have the help. I wasn't getting the help that I wanted from the people around me. I only got the help from outside my country, from America, from England, from anywhere but Romania. And this is the truth. This is the naked truth. This is what my life was, and it still is. Yeah, I don't have access to outside, only here, only in this hole that is called Romania. Yes, let's not get into other subjects because the movie is long as it is. So I will stop here, and I will thank you very much for your attention, for your understanding, appreciation, and for your likes that you will click, and your consideration, and the kind words that I will receive from you in the comments. I hope. As you can observe, I'm not adding any advertisements in all my movies. I am just a general Joe, and I am Q12 after all. A general person. I'm not affiliated to anything and to anybody, and that's why I don't have that many likes on my YouTube channel and on my YouTube movies. Anyway, but the fight is not to gather likes, because that is a frivolity, that is an imbecility from my point of view. That's not really what I'm here for. I'm here to expose the way I'm thinking and the way I'm doing stuff. And with this, I will thank you very much for everything. I really hope you like it. If you like something, please comment. If you didn't like something and you think I didn't cover something, please also comment down. I hope you learned something. I hope you get something out of this presentation, and I hope it helped you in some way. I hope it enlarged your knowledge of things and how things works, and how complicated, how apparently easy things appear to be, and how complicated they actually are when you get down to them, to actually make them. And yeah, it is a bit complicated, but it's doable. And yeah, thank you very much for everything, for watching, and see you later. And I say goodbye to you from your favorite artist electronist, Mr. Q12. Bye bye.